So these observations by the Oersted were carried forward by the many scientists at that time, and one of them was Lorentz. He gave a very precise experiment of the magnetic and electrostatic force, both the forces together acting on a charged particle which was moving in the presence of both electric and magnetic field. That is, Lorentz gave us the expression for the effect of magnetic field on the moving charge, and that is called as Lorentz force. It's quite a you would say that simple expression which would explain so many phenomena which we are going to see further in the chapter. So what was the Lorentz force? It is the expression for electromagnetic force, on a charged particle moving with velocity v in presence of both electric field and magnetic field. So you could see it's quite easy, but of course it was not easy for him to find out this expression just from experiments, but he did. That's why we still remember his name. So the total force has two components, that is, one component is called as electrostatic force and other component is of course called as magnetic force. As I have already discussed, that the magnetic effect or the magnetic force is another component of the force of interaction between two charges. It is the force between two charges, but one of the component was electrostatic and this is magnetic, and both of them together are called as electromagnetic. Very simple. So the Lorentz force was electrostatic force, as you already know. This is Q and this is E, QE. This is electrostatic force plus Q V cross B. This was the component of magnetic force. So we have already seen much discussion about the electrostatic force. We have seen the motion of charge in electrostatic force. We have calculated so many electric fields, but right now we will focus on the second component, that is magnetic force. Although I will take few questions in which we also consider the electrostatic force in problems, but the main focus will be to study this expression, which is V cross B. Now you might be wondering that how come this expression has come. So my dear students, we don't have any derivation for this force. These all are the given informations which are known to us from the experiments or from the detailed carried mathematical analysis by the great scientists. So we have to take these results as it is, and that is the most difficult part might be for you to absorb this formula, that how can I just believe on this thing. So it's assertively I am saying that the magnetic force and the electrostatic force together, which are called as electromagnetic force, must be determined using Lorentz force. So Lorentz gives us the expression for magnetic force as the Q times V cross B, and you can clearly see if I make a charge at rest, this V becomes 0. So there is only one component of force between the two charges, that is Q into E, because if the charges are at rest, this V will be 0. So from now on, if anyone asks you what is the magnetic force on the moving charge, I have to say on moving charge, because if the charge is static, then there will be no magnetic force. Magnetic force will apply only if there is a moving charge in a given magnetic field. So this is the expression for magnetic force. Let's proceed further. So the magnetic force, the expression for magnetic force is Fm is charge of the particle times velocity cross product with the magnetic field. So if I write the magnitude, you can see that this is q v b sine theta times n cap, F magnetic. So if I talk about the magnitude of the magnetic force, this is q v b sine theta, and the direction of magnetic force, this is n cap, which is right hand thumb rule. Now as you already know that any cross product of the two vector has a direction perpendicular to both. So from here we can conclude that first thing, that the magnetic force is always perpendicular to both magnetic field and velocity of the charged particle. It's quite interesting property that this force is not along field, as we have seen in electrostatic forces, which were either along the electric field or were opposite to the electric field. But in this case, this is one of the most important property, that the magnetic force is not along the magnetic field. And that's why generally sometimes we'll see in future that we cannot call the magnetic field lines as the magnetic force lines. The field lines may represent the magnitude, the density of field lines may represent the magnitude of the magnetic force, but the tangent to it does not represent the direction of force, because the force is perpendicular to the field lines. In previous chapter we have seen the electric field lines are also called as electric force lines, because their densities as well as their directions both gives us the direction of electric force. But that is not the case for magnetic field lines, and that is why we cannot call them as magnetic force lines, because again I am saying the magnetic force is perpendicular to magnetic field, it is not along magnetic field. That's why this is one of the important difference, as well as velocity. Now second important thing, the magnetic force is always perpendicular to velocity and field. If something is always perpendicular to velocity, if the force is always perpendicular to velocity, we can say that the power delivered by the force is zero, because the formula for power delivered is F dot V. So the power delivered by magnetic force will be equal to F dot V, F magnetic, which is always zero. This is also one of the most important concept, that the work done or the power by magnetic force is always zero. Magnetic forces cannot do work, they cannot transfer energy. Then what will they do? They can only change the direction. If the particle is moving in a straight line, it will change, it will make it circle, it will make it helical, but it cannot increase its speed, because the force is always perpendicular to velocity. Whatever the velocity will become, the force will become perpendicular to it. Whatever is the direction of velocity, even during the motion, the force will make sure it is always perpendicular to it. It will never be along, never ever be along the velocity of the particle. So in other words, the work done by the force, magnetic force, is always zero, always, irrespective of the path. Okay students, so these are the two most important properties. One is force is perpendicular to both B and V. Second, the work done by magnetic force is always zero. Now about the direction, you already have known that how to calculate the direction of a right hand of a cross product. We calculate this direction using right hand thumb rule. We place our right hand in the direction of the first vector, which is in this case is A, and curl our fingers towards B. Then the direction of thumb will give us the direction of cross product. So with this basic important concepts, let's solve few problems and proceed.